Ruben Casas. I'm a biomedical engineering student here at San Jose State University. Today, I have the privilege and honor to introduce to you Dr. Michael Harrison. Our next invited speaker is not only known as a researcher, but he is also a professor, an author, and a clinical director. In 1984, he published the first comprehensive textbook on fetal therapy called The Unborn Patient. He is renowned for his expertise and innovation in pediatrics and fetal surgery. Dr. Harrison is a cum laude graduate of Yale University and went to receive his MD, magna cum laude, at Harvard Medical School. He completed his general surgical residency training at the Massachusetts General, and finally his pediatric surgery fellowship in the Ricochet Hospital at Oslo, Norway, and the Children's Hospital of Los Angeles. On the clinical forefront, Dr. Harrison collaborated closely with obstetricians, geneticists, subsurgeons, sonographs, and ethicists to lay the foundation of what will become the multidisciplinary UCSF Fetal Treatment Center. He is currently the director of the UCSF Pediatric Device Consortium and most recently been recognized as 2013 Physician of the Year. This morning he comes to us to talk about his journey from fetal surgery to the UCSF Pediatric Device Consortium. Without further ado, please help me introduce the father of fetal surgery, Dr. Michael Harrison.
Thank you, Ruben. So, Gunnar, I'm very sorry to say that I cannot return my badge. No, the reason I can't return this badge is I'm going to frame it, because it's the first time I've ever been conferred a PhD, which I don't deserve. Yes, thank you, students, for giving me that PhD. So I'm going to come and tell you some stories sort of from the other side of innovation, that is the medical side of medical devices. We'll have to innovate about how to get that thing back in here. So the medical side of medical devices. So I'll tell you a few stories, and again, this is, we'll start, oops. So this is going to be a little bit about the motivation for innovation. Again, the medical needs, the needs analysis that Dr. Vale talked to you about, and a little bit about some of the barriers that you will face and that we've faced in the past with regulation. So here's a couple of quick stories. The first one is odd. It's the story of fetal intervention. But it started 3 decades ago when we first could see inside the human uterus. Remember, in all of history, no one had ever seen an actual living human fetus until our buddies with these marvelous sonogram machines and all kinds of new imaging technology came along and showed us the fetus. And we noticed that the fetus was, like the babies we see after birth, sometimes had problems, and the problems looked like they might be fixable, and it made us think, oh, like all, docs, we want to help out. So to do that, we'd have to reach inside the uterus to try to help the fetus. But there were huge barriers to that, monster barriers, not the least of which was maternal safety. It's, as I was reminded many times when we were trying to start this, it's the only procedure in which you can have a 200% mortality. So we took this maternal safety very seriously and set up all kinds of bars that we would have to meet in order to do the first human fetal intervention. And most had to do with protecting the mom, who, after all, was an innocent bystander, was going to take on some risk to help her baby's chances. So now to get to the device part. So here we were trying to think, how are we going to do this thing where we reach inside the uterus? No one had ever done it before. Well, there were probably 20 or 30 steps, many of them involving devices that had to be solved, usually in the animal lab or some preclinical setting, before we could dare to do it in a human. And they're summarized on this slide, and I won't go through all of this for you, but on that slide are probably 20 things that we worked years and years and years to develop. New stapling devices, new retractors, new monitoring devices, all kinds of fun things. And to do that, and here are a couple of those devices illustrated, to open the bloody uterus, we had to get away from sutures, and we had to have staples, and it turned out that metal staples, which were available at the time, were no good because they made the mom sterile. Thank God we found that out in monkeys before we did it in humans. And so we had to come up with absorbable staples, the first ones. And all kinds of technical things like retractors and stuff. Or here, a good example, and this is just to illustrate how fun it was to innovate in those days, because we basically said, oh, we want to keep track of the fetus after he's back inside. It's, you know, you wouldn't do a huge operation on a patient, put him in a corner, cover him up with a blanket, and never look at him. So we went to NASA and said, oh, we want to have a radio telemeter that we put on the fetus during the operation, put him back inside, and then come up to the mom later with a big old antenna that we invented, and keep track of the fetal heart rate and the fetal EKG. And we just did it. So here's putting in that radio telemeter. Here's a baby born with the radio telemeter under the skin, sending out a signal. Now remember, this is 30 years ago. And guess how many permissions and approvals we got to do that? None, right? It was just a different world. It was before the FDA started to regulate devices and device development. So I'm just trying to make a point for you that hopefully you'll never have to suffer through, is that innovative treatment at the time was basically a covenant between the surgeon, the doctor, and the patient. And it was a very special covenant, and it essentially took the place of much of what we do now with huge committees and national consensus groups and all that stuff. If you had a covenant with your patient, you could do things very safely and correctly. So here are some of the things that came out of that work that was essentially pre-FDA regulation of devices. Lots of devices, essentially no problems in doing 30 years of totally new stuff, just right out of nowhere. We've never had a serious dispute with the family, whether we succeeded or failed. We've never had a suit. And so I think it can be done correctly and very productively without a lot of regulatory overview. Okay, that's the end of that story. There's a lot more in that story, but I'm using it just to illustrate the different areas of innovation. Now let's come up to, and that enterprise is very successful now, so there are lots and lots of those cases done around the world by very good folks with very good outcomes. I think we did 3 this week at UCSF, and it's great. But about a decade ago, I handed all that off to my wonderful young colleagues because I just wanted to do the device innovation that we had to do in that era, but to do it for other things. So we did this device consortium deal, and I'm going to tell you now about the device consortium, different story. So the first thing we started to think about was that we could solve some problems that we couldn't solve otherwise if we could provide a little bit of force over a long period of time to change anatomy. So here are a couple of examples of that. So one is pretty simple, sunken chest. So these are young kids who have pectus excavata, sunken chest. And to fix them, my whole career, we did these terrible, big, disgusting operations where we ripped the kid's chest apart in a big operation, put in steel bars and things to hold it, get it in the right place, hold it in the right place with a steel bar, come back a couple years later and take the bar out. It worked, but it was clearly, in my mind, not the right thing to do. The right thing to do would be, if you could have figured out how, would be to do it like an orthodontist does our kids' teeth. Would be to move it just a little tiny bit over a very long period of time and to thus remodel anatomy by mechanical transduction. And as a biologic principle, that flat out works in many, many cases. But of course, at the time, we didn't know how you could grab the sternum and pull without, having like a screw or some mechanical thing through the skin, which wouldn't work. So I thought of the idea of putting a magnet on the sternum, and the kid would wear a separate magnet on the outside, and it would gradually pull the thing forward over time and remodel the chest instead of breaking it. And in fact, and of course, if you just think about it, that would be pretty slight, because the present correction requires like a week in the hospital, epidural anesthesia, months with narcotics. It's miserable. And you could do this, in theory, as an outpatient. So we went to work on that. We had to solve lots of problems, because now we're in the era of FDA regulation. You have to prove a magnetic, a big magnetic field next to the heart is not going to do any harm. We did that with rabbits. We had to do lots of other animal studies. We had to do lots of testing that you guys are used to and are good at. And then we had to do our approvals. And here's this is my favorite slide. Now that I'm in a full-out war with the FDA. So you have to now go through this process that we did not have to go through in the development of fetal surgery, which is pretty daunting. And this will give you a feel for it. Can you hear me when I turn away from the, or is it? Thank you. So you have to get this investigational device exemption. That took 2 years, an immense amount of work by talented people. And then we have to do, in this case, we chose to go orphan product. It's another whole game. And then you have to, get a study funded. So we set up a trial and actually got it funded, amazingly, by the good side of the FDA, the orphan products branch. So they funded the trial. But here's just, I don't know if you've been involved in clinical trials, but they are daunting in terms of the amount of work that you have to do. These are the individual patient charts for the first trial of just 10 patients. And at the end of that trial, the 10 patients did, so here's some of the incredible paperwork. And at the end of that trial, well, here's what it took to get into the trial. The actual doing of the procedure is really fun. It's a little outpatient procedure, brief general anesthesia, small substernal incision, attach the magnet to the sternum. There's a magnet inside the kid. There's an outside device. And the development of all these things with our team was really, really fun. And all of it was good. To give you a feel for this kind of innovation, when we wanted a number of things for the outside device. We wanted, of course, the kid to be able to adjust the amount of force applied, right? Because then if it hurt or if it was uncomfortable, he could loosen it up by simply, and the mechanism we came up with, just put it in a can with threads, so you move it in and out. Great solution, the kids loved it. The actual making of it, that black can is a Home Depot shower drain. So I just went looking for a big threaded thing, and it happened to work perfectly. It's a little more sophisticated now, but the concept's the same. The next thing we wanted to do for the kids was to record how hard you're pulling, because then you could relate that to, biology, and whether the kid had it on or off, which you could do if you could measure pressure, temperature, right? So he puts it on, the temperature goes up, the body temperature, takes it off. So then, and then we initially put that on a little chip inside the outside device, and then we take the chip out and read it every month and get a readout like this, which was pretty fun for us because it's a compliance monitor, which is really what all orthotics need, is a compliance monitor. You want to know how much the kid is using it. By the way, we're working on one of these now for orthotic devices for your kids' teeth. So, but the fun thing about this is you saw the kid every month and you say, hey, how you doing today? Oh, great, I'm wearing it all the time. And you say, well, how about December 6th between 4 and 8 o'clock? Oh, yeah, a basketball game, or I had to take it off to take a shower or something. It's a great way to just keep track of kids. Since then, we've converted that. I'll finish up so we did those first 10 patients. It worked perfectly. It was safe. Everything was great. We went to the FDA and said, hey, FDA, let us get this out to our colleagues around the country. They're all waiting for it. And the FDA said, no, we changed our mind. We want you to do another study. We're in the middle of that second study now, 15 patients, multi-center. It's just incredibly painful and also unnecessary. That's my pitch. The kids actually had very good compliance. They wore these things like 90% of the day, which means they wore them at most of the day. And they had fun with their friends, sticking things to their chest, or their friends would throw their keys at them and they'd go, clunk. So it's fun to have an implanted magnet. So, and it works. It pulls the chest out over time. And we learned many, many things, as you usually do. And the most important one in this case is it matters when in the kid's life you do this. It's best, just what you guess actually, can be done when the kid's chest is relatively compliant. That is, before the rapid growth spurt of puberty. I want to show you this because it's what Brad Vail was talking about, is funding these things. We're on the lean launchpad side of this, so we do things extremely lean. We don't have venture funding or anything else. But here was this gives you a feel for what this costs. And the big arrow is, hey, if we would have just done our first trial, I think the blue is the FDA funding, and the rest of the red is our funding. We just sort of make up ourselves. And if we could have done it then, we would have finished it at a very reasonable price, less than $1 million. But by turning us down and making us go out to 2014 now, where we're just finishing up, it's going to cost $4 million. So regulation costs. So I was forced to stir up a little trouble at the FDA by writing in our peer-reviewed publication this statement about trials. You can read it yourself, but it wasn't complimentary. And it's also true. So there's the new trial. Here's the, oh, sorry, going the wrong way. Oh, really wrong way. Okay, and then the part that you guys would like is then you get to iterate about all your things. We iterated about how we attach the thing to the sternum to make it easier for the surgeon. We iterated about the outside device and the screw device. We iterated the electronics, the board on the inside. And the last iteration, I think I have on here, is this. We no longer have a chip on board. What we do is have a Bluetooth signal to the kid's cell phone, and then to the cloud, then to us. I hope to talk the FDA into letting us send the data, the raw data, to them, and thus do post-market surveillance on every thing, which I think is a big step off for the future. So the kids are now using this Bluetooth device. So we get to play, we get to innovate, we get to move the ball forward. Oops. Okay. And then you get to, so one final little innovation on this is, then you can gamify it. So not only can you measure compliance, but you could induce compliance by making a game out of it. The kid plays on his cell phone. And the ultimate compliance inducer is social media, right? So we plan through an outfit called Teatros to eventually allow patients to choose to hook up to other patients undergoing the same treatment. And then they'll have a little contest. How much did you wear yours today? I wore mine 95%. So these are fun things for the future. These are just the idea of gamification for the kids. And I think it probably has a big future. Now, Gunnar, you'll have to tell me. Okay, so that's one story. That's the end of that story. That's a lot of innovation, a lot of work for a very small market, right? This is not something that anyone's going to give us a lot of money for because it's a small market. It's a small, important market, but it's small. Here's something maybe not in a little different category. So, along the same idea of using magnetic force to achieve changes in biology, we came up with the idea of doing magnetic anastomoses. So at present, the way we as surgeons, I'm a pediatric surgeon, do anastomoses is either with sutures, that's how we all learned it, or now with wonderful stapling devices, beautifully engineered, wonderful, wonderful devices. So as Brad said, you know, when you, as a surgeon, you say, well, I have to do an anastomosis, nurse, sutures, nurse, you know, the Covidian staple device, or J&J staple device. And now there's going to be a third alternative, which will be the magnemosis. And the magnemosis has many advantages. So the concept here is it's fun. If you take two magnets and stick them together and, you know, to try to make an anastomosis, it'll fail every time. Why? Because it's flat to flat. It all has to do with the geometry of the mating surfaces. And that's why when your kid eats a magnet, you know, and they swallow these magnets that are all over now. If he swallows one, what happens? Nothing. If he swallows two, what happens? Nothing. Because they're stuck together. They're just bigger. If he swallows one today and one tomorrow, what happens? He dies. The reason is the magnet starts down the GI tract. Now it's in a different part of the GI tract. A new one comes along, they smash together, and they make a hole. But if you engineer the mating surfaces, you can assure that every single time the inside will necrose, the inside of the deal will necrose, and the outside will heal. And it'll heal in such a way that it gives a better end anastomosis, end product anastomosis, than either staples or sutures. So, oops. So I didn't carry this any farther, but I'll just tell you where we are. So we've done all the preclinical work, 60 pigs, 0 failures, 5 monkeys for a totally new reason, which is we think we can cure diabetes with this. And we're set to do our first clinical patients next week at UCSF. I've done one of those pilot studies with 10 patients. So it's going to be, it should be fun. And now again, I promise I'll just show some of these projects because we're hoping to attract this kind of talent to our little group and to Shubo's MTM program, okay? And to our little pediatric device consortium where we hold open meetings twice a week, every Tuesday, every Thursday. You're all invited. We'd love to have people come and just talk about devices. So here's one of them, which is a robo implant. It's taking a dumb rod that orthopods use to either straighten up your spine or lengthen your bone and make it smart by being able to make it shorter or longer without reoperation. And we do that with magnetic coupling. And there's the outside device. So anyway, we want people to work on this. So that's one. Another fun thing about magnets would be curing sleep apnea. That'd be fun. So the idea here is that you take a little magnet and you attach it to your hyoid bone, and you then do what the kids do with their chest. You're just like everybody else during the day, it's not even noticeable, but at night you fall asleep and go, like sleep apnea folks do, because their airway collapses. You take our second little magnet cup, it attaches magnetically, pulls the airway forward, and you live happily ever after. I don't know if that story's going to come true, but pretty fun. We are making little magnetic devices to be adjuncts to our endoscopic surgeries, and that's a different kind of pectus, chest wall deformity, where the breastbone sticks out instead of sticking in. Remember, we're going to cure the one that sticks in with our magnet, and we're going to cure the one that sticks out. You don't need a magnet, you just need to push on it, but we'll add our electronic compliance measurement deal to that, and gamification. New ways to drain hydrocephalus, not magnetic. These are Shuvo's friends. And then Shuvo's artificial kidney, which is just a major assault on a huge problem. It's big and complicated, not like our little magnet projects, which are sort of a little one, not too complicated. But I think Shuvo told you about this a couple of years ago. I'll give you a feel for our Pediatric Device Consortium, which is this little group that again meets twice a week, every single week. And here's where we are with, looks like a dozen projects up there. We're trying to move them down the pathway to commercial use, and we're getting there, but it's a long but really fun pathway, and we hope that maybe some of you folks will want to come up and join us. So our Pediatric Device Consortium meetings are every Tuesday, 4 to 5, down next to Roy Shuvo's office in the new Mission Bay campus, and that's to attract the engineers and the scientists. And every Thursday morning, 8 to 9, on the clinical campus at Parnassus, where I hang out, and we want you to come up and visit us. I think I should end. Thank you so much.
Thank you, Dr. Harrison. That was fascinating. We have time for a couple of questions, if anybody has any questions. Going once, going twice. Oh, yeah, please use the microphone. If you can state your name and affiliation, please.
Yeah. Hello, my name is Francisco Bengi. I'm a graduate student here at San Jose State, general engineering, focused on bioinformatics. So my question is, how receptive are venture capitalists to open source biomedical devices, and also like open source biomedical devices that want to stay open source? Are venture capitalists reluctant to invest in that? Or do you have any biomedical devices on that list that are currently open source? Could you just discuss that?
I'm just trying to think of a way to go at it. Let me tell you what we decided to do when we got our PDC funded. We said, okay, what are we going to do about intellectual property? Because everybody in the past has sweated over this, and they all hide their little things, and they're all worried someone's going to steal stuff from them. And we said, we're not going to do that. We're going to do this completely open innovation. And so when you come to our meeting, there's no secrets. And if you don't want to tell us something, that's fine. But everybody signs a gentleman's agreement, probably is not to go after the other folks' stuff. You know what? It's worked perfectly. Perfectly. We've never had a dispute. We've had lots of intellectual property come out of it. Most of it goes through the arcane UC intellectual property system. We probably have 20 patents or something on all these different devices. And it works. So you're in IT, and you might have a different view of open source versus, I think of it as open innovation. What do you think of as open source?
It means that you could publish your device, how to make it online, and people could reproduce it freely if they wanted to. They could build their own.
We tell the folks who come to this thing, that we were happy to help in any way, and people jump in, oh, you gotta make that, you gotta do this. But when it comes to intellectual property, you're on your own. You do it, no one's, you know, if you want to include other people, you can, but just do it. And people do it. In terms of publishing our academic stuff, our meetings are wide open. There are no secrets. And all of our stuff is published in peer-reviewed journals. So there's none of that I know of, there's none of that game of having to sort of hide your stuff. I don't want to publish it, I don't want to tell it in a meeting now. I just don't believe in it. So I guess you'd argue that I believe in open source.
Thank you, Dr. Harrison. Just one more minute, please.
Dr. Harrison, thank you for that enlightening talk. On behalf of the BME Society chapter here in San Jose State, we present to you a certificate of appreciation, as well as a small token from us to you.